Okay, welcome to the next set of our mini lectures. Today we're starting to talk about detectors, or ways that we can take the photons and turn them into an electrical signal so we can actually do some measurements and go back to some electrical engineering. And here again we see our diagram of a spectrophotometer system with light coming from the source, being collected, going through filters, moving along, hitting a sample, which then fluoresces in our case. We collect that light, filter out the stuff we don't want, and hit the detector right here. So this is what we're going to talk about. The detector that's shown here is a schematic diagram of a photodiode, but today we're going to be talking about photomultiplier tubes. And photodiodes and photomultiplier tubes are the two types of detectors we'll be talking about in the class. So a photomultiplier tube is a type of detector that changes photons into electrons so they can be detected. And photomultiplier tubes are called photomultiplier tubes because they amplify the electrons. Of all the electrons that are generated from the photons, those electrons are amplified many times before you detect the signal. So let's see how that works. If we have a photon, and here's our little signal or schematic for a photon coming in with some energy h nu, that photon's going to come and it's going to hit a type of metal called the photocathode that technically has what's called a low work function. In other words, you can get photoemission of an electron from this by the energy of the photon coming in. And this is the photoelectric effect that Einstein won the Nobel Prize for way back in the early 20th century. And you've probably learned about this in your semiconductor device physics or modern physics class. Anyways, this photon hits essentially the electrons generated, and the electron sees an electric field because these photomultiplier tubes have very, very large voltages of hundreds or even thousands of volts across them. And that electron sees this electric field and goes through the focusing electrode and smacks into a dynode, which is a plate made out of material that if an electron comes and hits it, it can knock multiple electrons loose. An analogy would be, think of maybe a wall with a bunch of BBs stuck onto it with tape, and if you slam a BB into that wall at high speed, it's going to cause enough disturbance for a couple of those other BBs to fall off. Well, these electrons that are knocked loose from the dynode, and let's say you get 2 or 3 electrons, let's draw 3 here, are going to get accelerated to the next dynode. They're going to pick up enough energy with the electric field to knock multiple electrons loose from each of the electrons it hits, and pretty soon you have this cascade of electrons that comes, and what you collect here eventually at the anode is a huge number of electrons for every photon that comes and hits. And we'll learn more about how to do calculations with this in a little bit. But the general idea is that a few electrons generated at the photocathode are multiplied by many hundreds or thousands of times and collected at the anode. Of course, this tube, which is actually a glass tube, as we'll see in a picture in a minute, is full of vacuum, so the electrons don't smack into air molecules inside the tube. And the sensitivity of this, the amount of amplification, both depends on the voltage you put across it, how much acceleration or kinetic energy these electrons pick up from dynode to dynode, as well as the number of dynodes. And I think you'll have a nice little Java applet or Java tutorial you can go through and look at this in your reading assignment for today. So here's a picture of a photomultiplier tube. The one that's shown here is called a front-on photomultiplier tube, because the photons come and hit the front of the tube there. The photograph is one of the ones we actually have in our lab, and this is called a side-on, because the electrons come in the side of the glass tube rather than hitting the front. But the general idea is exactly the same, and these things work in exactly the same way. There's really, from an electrical point of view, no difference between them. If we look at the gain, the number of electrons, or the amount of gain we get from one electron being multiplied into many electrons, you can see at a voltage of 300 volts over here, you get a gain, typically it looks like on the order of about 400. So one electron is going to be multiplied into about 400 electrons if you put 300 volts across it. At 600 volts, this gain becomes 100,000. At 900 volts, we're talking about something on the order of 3 million gain. And so you see on this logarithmic scale, the gain increases very dramatically with voltage, and in fact the gain is proportional to voltage to some exponent, let's call x, and you can tell this immediately and calculate this exponent because on a log-log scale, a power law like this plots directly to a straight line, as you know. Okay, so let's look in a little bit more detail at how these photomultiplier tubes work. They change electrons into photons, we know, and photomultiplier tubes actually amplify the electrons. One of the things that's important about photomultiplier tubes from an engineering point of view, or a point of view of somebody who really wants to use them rather than the physics of them, is the sensitivity of them. And the sensitivity is given either in terms of amps per watt or quantum efficiency, and these are essentially two ways of expressing the same thing. And the quantum efficiency is the probability that a photon can create an electron, which will then get amplified and will be detected. And the specification of amps per watt is how many amps of current you get out of this thing for 1 watt of light. And the curves of this are shown here. So let's look over at our photomultiplier tube. You can see that the photomultiplier tube, we have the radiant sensitivity or the quantum efficiency, and the quantum efficiency is given by the dashed line and the radiant sensitivity is given by the solid line, peaks on the order of 300 nanometers to 400 nanometers. And you'll notice that this efficiency or the sensitivity falls off very, very rapidly as we start to get out into the red and infrared region of the spectrum, because those photons don't have enough energy to knock an electron loose, it turns out. So let's look at how we convert between a quantum efficiency or a sensitivity. And what we're going to do here essentially is look at the conversion, and then on the next slide we're going to do a calculation to see how much current we actually get out of one of these things for every watt or fraction of a watt of light that comes in. So quantum efficiency, and let me go ahead and change to a different pen color here so we don't have to look at giant red ink as we do these calculations. The quantum efficiency is defined to be the number of electrons that come off the photocathode and before they're amplified as a function of the number of photons that hit it. And let's take, for our case, the quantum efficiency at 400 nanometers down in the blue-violet region of the spectrum. Just by reading the curve here, we see the quantum efficiency looks to be on the order of 20% at 400 nanometers. Okay? The sensitivity is given in terms of the number of amps of current that come off that photocathode as a function of how many watts of optical power that hit it. Well, let's go ahead and expand this out. We know amps are coulombs per second, and coulombs, the number of coulombs is just the number of electrons times the charge on an electron. So the amps are given by the charge on an electron E, which is 1.6 times 10 to the minus 19 coulombs, times the number of electrons we have per unit time that I'll call delta T. The amount of optical power is simply the energy of a photon, hc over lambda, which we know, times the number of photons per unit time delta T. And so now let's go ahead and simplify this a little bit. Let me go ahead and get some red ink so we can basically see that these delta T's in the top and bottom are going to cancel out. I've got nothing else that looks like it cancels out right here. So let's go ahead. We've got E. And let's go ahead and put my NE somewhere else. I've got a lambda on the top here because that's going to convert. I've got an HC, and then the number of electrons on the top, and the number of photons on the bottom. Well, we see that's just equal to the quantum efficiency, so we can write our sensitivity in terms of amps per watt being equal to E lambda over HC times the quantum efficiency. So that's how the sensitivity and quantum efficiency are related, and you can go ahead and do these calculations fairly simply. Let's go on and look at actually doing some measurements with the photomultiplier tube and look at the effect of noise, because no detector is perfect. Your limit is always